As we all know, the history of life is embedded in rocks as fossils, which can be used to observe the characteristics of organisms that are no longer living today, and we can use that to compare and contrast the morphology that they share. While fossils are a great way to determine the morphology of organisms, they aren't 100% reliable for determining how certain species are related to one another. That's where DNA analysis comes in, and you can find out how closely related certain species are to each other, and whether they are related at all, or if they just went through homoplasy and developed the trait on their own independently. While fossils make it easier to compare traits among organisms, they can be quite difficult to find, mainly because there are certain conditions that have to be met before a fossil will even form. First and foremost, the organism has to die and the corpse must end up in an environment with water so that the mineral exchange can occur. Secondly, the corpse has to be covered in sediment to prevent scavengers from feeding on it. This is very important because when scavengers start feeding on the corpse, the body parts begin to disperse and the fossil is no longer intact. Then the corpse has to go through the process in which the bone is replaced by minerals, which can take millions of years, thousands of years. Lastly, the fossil has to be exposed by the elements when it is embedded in the rock so that it can be discovered by a person that just happens to walk by. But also because of these conditions and the fact that soft tissue is quite uncommon to find as in fossil form, the fossils of land-dwelling organisms are less common than the fossils of marine organisms. This is due to the fact that the organism has to be in a water-based environment, and usually land-dwelling organisms aren't found dead in water-based environments. Alright, now let's discuss the differences between igneous rocks and sedimentary rocks. Igneous rocks are formed by the cooling of magma, usually when a volcano erupts and the magma cools down and hardens into rock or crystallizes. Sedimentary rocks are made up of strata, which are later layers made up of sediments. And because of this, fossils are found in sedimentary rocks since sediment has to cover a corpse for it to form into a fossil. Radiometric dating. To determine the age of rocks, a process called radiometric dating was created in the 1940s. The process helps one determine the age of a rock by using radioactive isotopes and the amount of half-life it has gone through in its lifetime to determine the age of the rock. And a quick description of a half-life is the amount of time it takes for the isotope to fall to half of its original value. These usually take thousands of years, millions of years, or even billions of years, depending on the isotope that is used. Alright, now let's try a practice problem on how radiometric dating works with fossils. Scientists found a fossil bone from an organism in a deep layer of rock. When they took the bone back to the lab, they realized that the bone only had 1/32 of the total carbon-14 left. Based on the amount of carbon-14 left, how old is the bone? The half-life of carbon-14 is, of course, 5,730 years. The first step is to identify how much carbon-14 is left. As stated in the problem, 1/32 of the total carbon-14 is left in the bone. Secondly, we have to determine the number of half-lives carbon-14 has gone through. We do this by starting with a half-life, which is technically half of the isotope is left. So after that, you take half of the half, and you get a quarter of the isotope is left. Half of a quarter, an eighth of the isotope is left. Half of an eighth, 1/16th of the isotope is left. And then half of a 16th, 1/32nd of the isotope is left. And from this, you can conclude that carbon-14 went through 5 half-lives. Lastly, you multiply the number of half-lives by the time needed for the half-life to occur. And since the carbon-14 has gone through 5 half-lives, you multiply 5 times 5,730, and you get 28,650 years old. And thus you conclude that the bone is 28,650 years old. And now we get to transitional forms, which are organisms, some which have been discovered in fossil forms recently that fill important gaps in the fossil record. These transitional forms make it easier to see the connection between organisms since they are able to show certain traits in their beginning stages that, even though they are not fully developed yet, you can see kind of how fins became legs in the process. Examples of transitional forms are Tiktaalik and Archaeopteryx. Tiktaalik and Archaeopteryx are important transitional forms since Tiktaalik shows the progression of marine organisms to land organisms, and Archaeopteryx shows the relationship between reptiles and birds. The fossil of Tiktaalik was an important discovery, as mentioned previously, since it shows the transition of marine life to life on land. While Tiktaalik had gills for breathing underwater, it also had lungs which gave it the ability to breathe out of water, and thus it can search for prey out of water, and thus had better chances for survival. In addition to lungs, Tiktaalik had sturdier fins which allowed it to walk on land, which its predecessors did not have. Descendants of Tiktaalik showed a more developed fin, which is even sturdier than before, and made it easier to walk on land, and eventually the fins became feet, and Tiktaalik became more commonly known as the crocodile. As you can see from the morphology, it kind of looks like a crocodile in this state. It just does not have fully developed legs, and it still has gills. While Tiktaalik's discovery led to evidence that life came from the ocean, the discovery of Archaeopteryx provided evidence that birds are related to reptiles. Archaeopteryx shows the transition from which some dinosaurs which had feathers and used it for insulation, and how feathers became useful for yet another use, which, as we all know today, is flight in birds. Archaeopteryx showed the transition since the arms became more wing-like and the fingers fused together to provide even more use as wings. Another change over millions of years, which are not apparent in Archaeopteryx but in birds of today, is the position where the neck connects to the head. In dinosaurs and Archaeopteryx, the skull connects to the neck from behind the head, and in birds, it connects from below the head. And that covers transitional forms.
Origin of birds. Biologists and paleontologists tell us that birds evolved from reptiles. In the image on the right, you will notice two species from different time periods. On the right is a present-day chicken, and on the left is a Microraptor gooey. These two share the physical features of opposable toes and feathers. Microraptor gooey possess jaws with teeth, claws, separate fingers on wings, and a neck attached to the back of the head. As time passed, their teeth disappeared, the claws and fingers fused together, and the neck lowered to the bottom of the head. These creatures also developed hollow bones and large breastbones to allow for flight. The path to flying was not simple or quick. The animals must first learn to glide and must use airborne hops to strengthen their muscles and increase their ability to travel long distances. The reason for the development of feathers is unknown. The purpose for insulation could play a factor. Unlike other reptiles, these animals were warm-blooded, and the feathers could have helped regulate their body heat. Escaping predators and catching prey were also other reasons for feather use. Evolution of whales. It is not certain about the evolution of whales. Biologists have learned that the closest living relative of whales is a hippopotamus. They made this prediction by comparing the DNA and the shape of the pelvis of both creatures. The ancestors of the whales were land mammals. In fact, during paleontologists' expeditions to locate the missing link for whales and hippopotamuses, another discovery was made. To the right is Indoeus, the cousin of the whales. They both have similarities in their ears and teeth structure. The reason for the whales returning back to the water is unknown. It was predicted that once the dinosaurs became extinct, there were no longer dangers in the sea. The whales could return to the water and there was abundance of food. What the fossils tell us. There are three things that we can learn from the fossils. First, the rocks speak out loud about evolution. They show that evolution is a must to adapt to habitats, unless the environment is stable in which there is no need for change. Second, we locate forms that transition over time. Lastly, there is evidence that creatures evolve from old to new.